Alright guys, you'll remember that there was a whole bunch of trig questions from the homework that we never got a chance to discuss in class, so I decided I would post some video solutions to those problems that we didn't have time to discuss. So page 625, this is one of the fundamental trig identity homework questions where we need to prove this identity. And wow, that looks pretty complicated, doesn't it? It's tempting to try to cancel this factor with this factor, but of course I can't because the numerator hasn't been completely factored with the plus 1 at the end. You can only cancel on the top and the bottom when the entire top and the entire bottom have been expressed as a product of things, and here we've got a sum of things. So I'm not able to do any cancellation. I'm just thinking about my other techniques here. I'm not able to factor. I'm not able to find a common denominator because I'm not adding or subtracting fractions. Sneaking a peek doesn't really help me on the other side, other than to show that I end up with something really quite simple when I'm done. So I'm actually a little ashamed to admit it, but I think I'm going to resort right to the hammer method of converting everything into sines and cosines and seeing what that does for me. So my left-hand side then is going to become a 1 over cosine v minus a sine v over cosine v. I'll notice that there's a common denominator there of cosine that could be useful momentarily. And here I've got 1 over sine v multiplying by 1 over cosine v minus 1 over, minus sine over cosine v. Again, I can see a common denominator of cosine, which might prove to be useful. So if I use this common denominator idea, then I've got 1 minus sine v all over cosine v, which is being squared. Clearly, I'm going to end up getting a cosine squared in a moment in the denominator, so I'm just going to convert this right now to a cosine squared over a cosine squared to anticipate having a common denominator to add. And down here I've got my 1 over sine v is multiplying a 1 minus sine v over cosine v. Alright, let's keep going then, and so I'll square the top. Let's expand it carefully. It gives you 1 minus 2 sine v plus sine squared v. And you remember that this is over cosine squared v, so I've now got a common denominator. And I can put everything over that cosine squared v. And in the denominator, I've got my 1 distributing to a 1 and the negative sine v. And we're dividing everything through here by sine v cosine v. Okay, now sine squared plus cosine squared, you might notice, is equal to 1. So that gives us a total of 2 in the numerator, minus 2 sine v, all divided by cosine squared v. And I'm going to multiply by the reciprocal of the denominator, sine v cosine v over 1 minus sine v. Immediately we can see that a factor of cosine will cancel on the top and the bottom. If I factor the 2 out of my numerator here, I'm left with 1 minus sine v. And as I multiply by my second expression, I realize that I can cancel this factor of 1 minus sine v from the top and the bottom. What I'm left with then is 2 times sine v over cosine v, which of course is 2 times the tangent v. And that's my right-hand side, so I'm done the proof. Number 82. So let's start with my left-hand side and try to transform it into the right-hand side. I've got a sine cubed plus a cosine cubed. That's a sum of cubes. So I'm immediately tempted to try to factor that out and see whether that will help with anything. At this stage, I think it's just really experimentation, but we'll see how we go. So my sine theta plus cosine theta would be a factor. My other factor would be sine squared minus, that's wrong, we're going to subtract just one sine theta cosine theta, and then we'll add on the cosine squared at the end. So there's the factorization of the numerator of the left-hand side. The denominator, I don't know whether you can see this, but it's the opposite of 2 cosine squared minus 1, which I recognize as one of my cosine of 2 theta identities. Yeah, looking at this again, I'm not certain that's going to help me any. So I actually don't think I'll factor out the negative 1 in retrospect. Let's just leave it as is and see what happens. Now in my numerator, I notice I've got a cosine squared plus a sine squared. That equals 1. So I've got now sine theta plus cosine theta multiplying by a 1 minus sine theta cosine theta. Well, boy, don't really see what to do here. So, yeah, I'm just considering right now expanding the top, but that's going to give me 4 different terms, and it might get even more complicated. I can't factor the denominator. Well, yeah, it's not very elegant, but at this stage, with everything expressed in sines and cosines, I'm wondering whether I should start working on my right-hand side and see whether I can kind of make them meet in the middle. So certainly not the most elegant of proofs to do this, but let's see if it helps. So let's first convert everything into sines and cosines. And now then I'll find a common denominator. So I've got 1 minus sine theta cosine theta all being divided by cosine theta. And in my denominator, I've got sine theta minus cosine theta all being divided by cosine theta. Well, I guess my cosines are going to cancel, aren't they? You can imagine if I took this fraction and divided it by the reciprocal of this, that my cosines would end up cancelling. So now I've got, well, this is interesting. There's my 1 minus sine theta cosine theta factor. If I could just get a sine theta minus cosine theta into the denominator there. Thinking. I see what to do. Okay. I'm going to replace this cosine squared. Sorry, let me start again. I'm going to replace this 1. So let me just write up my numerator as is. I'm not going to change anything in the numerator. Alright, in my denominator, and by the way, I'm doing this because I can see that my denominator has got just sines and cosines, nothing else. So maybe if I express this as, say, let's change that 1 into a sine squared plus cos squared. And then I'm subtracting my 2 cos squared. So I've just changed my 1 into this. And this simplifies, of course, to become a sine squared minus cosine squared. So I've now got a sine squared minus cosine squared, and there's a difference of squares. And so my denominator is now going to factor into a sine plus cosine and a sine minus cosine. And my sine plus cosines will cancel, and look what I'm left with. I'm left with exactly what I'd hoped to get on my right-hand side. 1 minus sine cosine all over sine minus cosine. And because my left-hand side is now equal to my right-hand side as I transformed each one independently, that's how I conclude that my original identity must hold true. Sine cubed plus cos cubed over 1 minus 2 cosine squared is equal to secant minus sine theta over tangent theta minus 1. And the only other proof from page 625 that we hadn't yet got a chance to discuss was number 87. Now, let's look through our different strategies. Should we convert everything into cosine and sine? That's already been done for us. Can we see any Pythagorean identities? Nope, because there's no square terms. Can I factor? No. Can I find a common denominator? No. I'm down to my last strategy, which I call sneak a peek. So I'm going to have a look over at the right-hand side, and I notice that I've got this factor of 1 plus cosine in the numerator that I would really like to have in the numerator here. Or perhaps you could argue that we should artificially inject a factor of sine theta into the denominator. So let's start off. Here's my original expression on the left. So I'm going to artificially inject one of these two factors. I'm not really certain which one is going to be the best one to inject. Perhaps I'd be best off injecting the simplest one. Thinking about that. Actually, I'm going to inject the more complicated one. So if I multiply the top and the bottom by 1 plus cosine theta, that's just equal to 1, so I haven't changed the value any. Now, this is important. I'm not going to expand the top. And the reason I'm not going to expand the top is because I want this 1 plus cosine theta factor to remain intact. I'm hoping that it's this other big factor which is going to cancel with the expansion of the denominators. So my 1 multiplies each of those terms. My sine theta multiplies each of those terms. And my cosine theta multiplies each of those terms. In fact, it's a negative cosine theta, so it becomes negative cosine minus cosine squared. Right, well, the positive cosine and the negative cosine are going to cancel. So let's have a look at what's left. I've got a 1 plus sine plus a sine cosine minus a cosine squared. I wonder whether I can do factoring by grouping here. I suspect that I can. I'm going to rewrite my numerator as is. Because remember, I'm still hoping that I'm going to be able to cancel with the trinomial I've just finished writing. And there's the factor I don't want to touch because that's how my right-hand side looks in the numerator. Here I'm going to do factoring by grouping. So between my 1 and my sine theta, there is no common factor. Let me just pull out a 1. 1 plus sine. Oh, I'm so silly. I'm going to start over on my denominator. I just noticed something. Remember how we're supposed to look for Pythagorean identities? Check this out. I've got a 1 minus a cos squared. What's 1 minus cos squared? It's sine squared. So, I've still got a sine theta and a sine theta cosine theta. And now I can factor out sine theta from my denominator. And so I'm left with sine theta plus 1 plus cosine theta. Oh look, that's familiar, isn't it? That's what's going to cancel with the trinomial 1 plus sine plus cosine. It's in a different order, but it doesn't matter. And I'm left with 1 plus cosine theta in the numerator. Therefore, I have proven my identity because I have achieved the goal of getting my right-hand side. Alright, these are the solutions to the only problems that we hadn't covered in class from page 625.